Hello, everyone. Thanks very much for your attendance. My name is Peng, a PhD student from Purdue University. It is a great honor for me to be here presenting our work, USBFuzz, a framework for fuzzing USB drivers by device emulation. This is a joint work with Professor Mathias Peng, affiliated with the EPFL. Testing drivers is challenging because drivers usually depend on the underlying hardware device, and it is very hard for real hardware to generate unexpected inputs during testing. In recent years, actually, there are many reported attacks and CVEs triggered by malicious inputs from the device side. However, on the other hand, existing defense mechanisms against malicious devices are limited. For example, rule-based authorization policies like USB guard and USB firewalls like LBM, USB filter can only detect known bugs and may potentially miss unknown ones. Other isolation-based approaches like Cinch rely heavily on hardware features and are very expensive, thus they are not used in practice at all. An alternative to defense mechanisms is finding bugs and fixing them. Fuzzing is a widely used approach to automatically find bugs in software and has been demonstrated to be very effective in recent years. In this work, we propose a framework to apply fuzzing on USB device drivers, which is the most widely used type of devices, because fixing bugs is better than passively defending against their exploits. Before I proceed, I would like to define our threat model. We assume that a USB device site is under the control of an attacker, either through a prepared device connected to a physical device or hijacking a connection to a networked interface run by, for example, a USB redirection server. Here, we only focus on unexpected data read from the device side. Under this threat model, a key challenge for USB fuzzing is feeding random device input to the drivers. There have already been some existing approaches to address this challenge. For example, UMAP uses Face Dumper, a dedicated USB device, to achieve this goal. This approach incurs hardware cost, and as one such board can only be used to fuzz one instance, this is not scalable. Other work, like sys-caller USBFuzz and Periscope, inject random device input at a certain layer of the I/O stack. Their implementation are usually tightly coupled with a certain OS version and cannot be easily ported to other operating systems. And as it is not an end-to-end approach, there are some code paths that are not covered. There is some other work trying to inject device data through the networked USB interface, for example, USBF, but it only supports dumb fuzzing and not able to leverage state-of-art coverage-guided fuzzing, which has been proven to be not more effective. In USBFuzz, we use an emulated USB device in the virtualized kernel to feed random device inputs to the drivers under test. And to support coverage-guided fuzzing, a host memory area is exported to the guest system so that coverage information can be saved. Compared with existing approaches, as a software-based approach, it is cheap and scalable. As it works in the device layer, porting to other operating systems is straightforward. Additionally, it also supports coverage-guided fuzzing. Here, the overall design of USBFuzz is shown. A guest VM runs the target system containing the driver that we want to test. A fuzzing device in the guest system is responsible for forwarding the further generated inputs to the drivers when I/O operations are performed on it. The communicating device exports a memory area in the fuzzer to the guest system so that the guest system can record coverage information. And the user mode agent component running in the user space of the guest system communicates with the fuzzer. The fuzzer is run in the host operating system and controls the execution of tests. If coverage collection is supported by the guest, it also connects coverage information. In USBFuzz, a test is started by further virtually attaching the fuzzing device to the guest system. Then the drivers are tested when performing I/O operations on the fuzzing device. The user mode agent detects end of test and notifies the fuzzer of it. Then the fuzzer finishes a test by virtually detach the fuzzing device from the guest system and continues to the next iteration. In evaluation, we first applied coverage-guided fuzzing on Linux by adapting K-curve, the static coverage connecting tool supported by Linux kernel, while fuzzing other operating systems like FreeBSD, Windows, and Mac OS. As coverage connection is not supported, we apply dumb fuzzing on these operating systems. Considering that they share the same input format, we use the inputs generated when fuzzing Linux kernel as seed. So far, we have found 26 new bugs in Linux and 16 of them are memory bugs of high security impact. On FreeBSD, we found one bug in the USB Bluetooth dongle driver. On Windows, we found 4 bugs, resulting blue screen of death on both Windows 8 and Windows 10. On Mac OS, we have found 3, with 2 of them resulting unplanned system restart and 1 resulting system freeze. We have failed 10 CVEs, and the CVE numbers are listed here. We also measured the test speed of USBFuzz and found that the throughput is relatively low, ranging from 0.1 to 3.0 executions per second. We have analyzed the breakdown of test execution time and found that most of the time is spent on OS device interaction. Similar throughput is also observed in syscaller USBFuzz. Here, we showcase a bug that we found in the USB core framework in Linux kernel. In the USB standard, devices are described using some data structure called device descriptor. There are many types of descriptor of varying length, so the standard defines the first 2 bytes to represent the length and the type of a descriptor. All legitimate descriptors should have the correct length and type fields. And the device descriptors are read from the device when a USB device is attached to a computer. We found a bug in one of the functions for parsing such descriptors. As shown here, the vulnerable function determines the type of a descriptor using untrusted data read from the device side. If the device is under the control of an attacker, he or she can masquerade non-descriptors using short ones. Leveraging this vulnerability, the attacker can trigger out-of-bound memory access. For example, if the attacker provides these 2 bytes from the device side, it will be accepted by the vulnerable function at a 3-byte USB OTG descriptor. So when the missing field is accessed, out-of-memory access is triggered. Here, we demonstrate a bug that we found on Windows triggering blue screen of death. On the right-hand side, a running Windows system is in a knocked-off state, and we attach the fuzzing device with prepared input. Okay, then the Windows system crashes with a blue screen. Here we showcase another crash that we found on macOS resulting unplanned restart. Similarly, the running macOS system is in a knocked off state, and we attach the fuzzing device with a prepared input, and then macOS is restarted automatically. To conclude, testing drivers is challenging. In USBFuzz, we provide a device emulation-based approach to first test the USB drivers. USBFuzz is a cheap, portable, and flexible framework. So far, USBFuzz has found 26 bugs in Linux, 1 bug in FreeBSD, 4 bugs on Windows, and 3 bugs on macOS. The source code of USBFuzz will be released in this repository. And with this, I'm going to conclude this presentation. And thanks very much. Now I'm open to questions and comments.